Diana, thank you so much for this kind introduction. And also thank you and the Croatian Physical Society for the invitation to be with you today and to give you an update on LSST and Rubin Observatory. I was pleased to learn that the Croatian Physical Society includes not only professional scientists, but also students and teachers in schools. So I designed this talk to give you a broad overview of the project itself, of the motivation for it, and broad overview of very diverse set of science goals that we have for LSST. So I will not go super deep, but I do want to touch upon all the scientific motivation that we have for the project. So before I start, all right. Before I start, let me just talk few seconds about the name. Until recently, the name of the project was the Large Synoptic Survey Telescope. But in January, the name was changed. And so the observatory is now named after Vera Rubin, who was the first astronomer to provide convincing evidence for the existence of dark matter in the 70s by measuring the rotation curves of spiral galaxies. So the actual building, the system, the camera, the observing system is called Vera Rubin Observatory. And the first 10 years of Rubin Observatory life will be dedicated to a new survey of sky that is called the Large Survey of Space and Time. You can see it's the same acronym LSST, but it's not Large Synoptic Survey Telescope anymore. It's Large Survey of Space and Time. So we kept acronym for various technical reasons. But now we distinguish between the first 10 years of the observatory and the observatory itself. So we were hoping to start in 2022 before the COVID shut down. Now the beginning of the survey will probably shift to 2023. So I'll start with very brief introduction to what LSST is about. Then I'll talk a little bit longer about the 4 main LSST science themes that drove the system design, that still represent the main reasons for executing LSST. Then I'll show you a bunch of pretty pictures of the components of the system and give you construction status update. And depending on how we do with time, how many questions perhaps we get along the way, I'll briefly comment on what is ahead of us once we have this data set. What do we need to learn and what we will need to do to accomplish science that I will be talking in the first part of the talk, assuming that we get the data from LSST. So I plan to talk for perhaps 55 minutes or so, and then we'll have at least half an hour for questions if people want to hang around. But again, please feel free to interrupt me at any point in the talk. So here I have a collage of 6 major new observatories that are being built around the world. The 2 are space observatories, WFIRST and JWST. They are essentially successors to Hubble Space Telescope. Indeed, WFIRST has exactly the same size of the primary mirror, 2.4 meters. But what WFIRST will have and Hubble doesn't is 100 times larger field of view. So with WFIRST, you will be able to scan the sky 100 times faster than Hubble. Indeed, Hubble, all those beautiful images that Hubble obtained, they all can fit into an area on the sky a few times the full moon. So Hubble didn't cover a lot of sky. And WFIRST is planning to obtain survey of the sky that it might match LSST in size. JWST wants to push Hubble by building bigger mirror. So the collecting area is about 7 times larger. So it will go to given sensitivity 7 times faster, but it will have exactly the same field of view as Hubble Space Telescope. So very tiny. So WFIRST is survey instrument, JWST is instrument to look at particular objects, small area on the sky, and then being able to detect them in infrared wavelengths and go very faint. On the ground, we have these 3 huge telescopes, TMT, GMT in the States, and European ELT, which will be the largest telescope, optical telescope in the world with 40 meters. They are all similar to JWST. They all have very small field of view and cannot cover the large area of the sky. So you can see LSST, or it should be called the Rubin Observatory now. It's tiny compared to these other 3 ground-based telescopes. So you may ask, why do we need LSST when we have those three big telescopes? And the answer, of course, is field of view. What distinguishes LSST from these other three big telescopes is its very large field of view that is over 100 times larger than any of these other three big telescopes. And so LSST can scan the sky 100 times faster than these other telescopes. And that makes it a survey instrument. And once you have this large field of view, and here is comparison between typical large telescope, Gemini South in Chile, US public telescope, has the same mirror size as LSST, but if you compare on the right field of view, the field of view of LSST is 300 times larger than Gemini South. So because of that reason, LSST can cover the sky much, much faster, and then it can obtain survey of the sky in only a few nights. And that's the basic idea behind LSST. That's our trade secret. And the way to get large field of view without optical distortions is shown on this slide. So the trick is to have three mirrors, not two, but three. And these blue arrows show how the photons, how the light would come into the telescope. So stars are above, then the light comes down and bounces off this outer edge, this annulus. That's our primary mirror. Then it goes up to the secondary mirror, then goes back to the central portion of the bottom mirror, which indeed is two mirrors together, primary and tertiary. And then after bouncing off the tertiary mirror in the middle at the bottom, it goes through three lenses. And then the camera will be put in the middle of that secondary mirror. I'll show you some real photographs later. But the trick to have large field of view with small optical distortions is to have three optical surfaces. That changes the reflection angles and allows you to control optical aberrations across the field of view. So given this instrument, what we want to do is basically to dedicate it first 10 years to do very uniform survey. Every night you obtain as many images as you can, about 1,000 10 square degree images, and you do that every night for 10 years. That results in survey that is shown here in equatorial coordinates. The green part is the main survey. It will have about 800 visits, where visit is one image that with open shutter time, exposure time of 30 seconds. That's what we call visit. And that covers 10 square degrees on the sky, which is roughly 40 times the area of the full moon. And so the idea is pretty simple. Let's make the greatest survey of the sky ever, and then let's do various science. In practice, what we started with was the science. We first defined what science we want to do, and then we designed the system and the survey to accomplish that science. That's how it happened historically. So I give you a reference in the bottom left corner. That's the LSST overview paper, which if you get interested in LSST and you want to have jumpstart, one entry point, that paper is about 30 pages. It covers all the aspects of the system and describes the science drivers. And then it also has a number of other references where you can go deeper if you want to study data management or software or whatever. So these 4 science themes that we use to design LSST are listed here. So they encompass essentially the whole universe. It starts nearby with the solar system. Then we extend it to our galaxy, the Milky Way. And then we go all the way to extragalactic astronomy, to cosmological studies of dark matter and dark energy. And because we will have 800 observations of each point on the sky along 10-year survey, we will then open time domain for very faint objects. We will be able to detect lots of variable stars and lots of supernovae and lots of asteroids, and I'll get back to that later. So these are the 4 main science themes, and we selected them in early 2000s in an iterative process that involved both astronomers and engineers, because this is also limited by technology and of course by funding. We could build 10 times larger LSST, which would cost $10 billion instead of $1 billion, but it's very unrealistic to hope that you could raise so much money. So it's usually in the early stages of the project, it's an iterative process where you drive the design using science, but there has to be some limit to what you can accomplish given the current funding climate. So that's what happened. And we ended up with these 4 science teams. And now almost 20 years later, we still believe that if we had to redo the whole process today, we would end up with very similar system and with very similar science drivers. So let me now tell you a little bit more about each of these 4 main science themes. Let me start with dark matter, dark energy in cosmological context. As you know, we've known for about 100 years that the universe is expanding since Hubble found the expansion of the universe. Over the last 2 decades, we also discovered that the universe, that the expansion of the universe is accelerating, and that was a huge surprise, that was unexpected. And then there were a bunch of other cosmological measurements, most notably the cosmic microwave background measurements that also improved greatly over the last 2 or 3 decades from the first detection of cosmic microwave background to today, where we have very precise measurements of spatial angular structure on the sky and many modes in the power spectrum of the structure. This image on the right shows the simulation of dark matter structure formation, which we measure indirectly through the distribution of galaxies. And so there is a huge body of observations that are very diverse at different wavelengths, very precise. And the good news is that today we have so-called standard cosmological model that explains all these observations. And that's amazing that we can have a relatively simple model with of the order 10 free parameters that can explain all the observations going from galaxy distribution in optical to cosmic microwave background. However, there is also bad news. Bad news is that in order for that model to work, we need to assume that the universe is dominated by a component that was named dark energy, that amounts to more than 2/3 of the universe mass energy density. And we have absolutely no clue what it is. If you ask theoretical physicists to predict what should be the energy density of that component, then the results are off by a factor 10 to 60. That's one of the worst mispredictions in history of science. So we don't know what dark energy is, but it's even worse. We don't even know if dark energy really exists. And that is because all these conclusions about dark energy and these models that explain observations, they all assume that our gravity model, the general theory of relativity, is correct. But if it is not correct, then maybe we don't have dark energy, maybe we just need to modify GR. And so if you assume theoretically that you have some modified gravity model, which is not GR, it is possible then you can show it theoretically that you can now assume that GR is correct, and you can always find dark energy with equation of state that we call W of Z to explain the data for Hubble constant. So measuring just Hubble constant as a function of redshift cannot tell you whether GR is correct and there is dark energy, or that GR is perhaps wrong and you can get away without dark energy. You also need to measure the growth of structure. And if you have precise measurements of the growth of structure, then you can break the degeneracy. And there is this, if you are interested in this topic, I highly recommend this review paper by Bhuvesh Jain and Zhu, which describes in detail how you connect modified gravity theories from theoretical side with practical things like astronomical observations. But important here is that astronomical observations and astronomical observations only can break the degeneracy between this curvature perturbation and the potential perturbation. So we can get measurements, observing constraints on these two. And we know that in GR, they must be equal. If measurements will show that they are different, then we know GR is wrong on cosmological scales. That's the idea. And so how can we measure it in astronomy? There are 5 fundamental probes. In optical, we can do 4 of them. So 3 of them are based on galaxies, weak lensing of galaxies, galaxy clustering, and baryon acoustic oscillations. They all rely on measuring the large-scale distribution of galaxies and their light and the formation of that light due to lensing. So for that, you need a lot of galaxies because they're statistical probes. Our goal is 1% measurements in LSST, and that immediately translates to the need for billions of galaxies. And indeed, our gold galaxy sample for cosmology has about 4 billion galaxies in it. That's why we need so many galaxies. And then on top of that, we'll also have a few million supernovae because they are excellent standard candles, so they're excellent constraint on Hubble constant. So to summarize this cosmological idea of LSST, we want to use cutting-edge probes based on galaxies in supernovae and optical to test whether the recent acceleration of the universe is due to dark energy within GR context or due to perhaps modified gravity, modified GR. So for popular talks, we usually summarize this part as we are asking, was Einstein right or wrong? And for the first time, LSST data will tell us what might be the answer to this question. But we already can illustrate how you would do it with the data. Indeed, there is a beautiful paper published about 10 years ago in Nature. It constructed quantity they called EG that combined different measurements of the structure growth in the universe with measurements of Hubble constant. And so then you can predict what the value of that measurement has to be within GR. And so in the diagram on the left, the x-axis is the scale on which you do your measurement. These are intergalactic scales. For example, 0.5 megaparsec is distance to Andromeda galaxy. So this is now already large cosmological distances, but still not gigaparsecs. And the measurements from SDSS and other surveys are shown as dots with error bars. And so the range that is allowed by the data is shown as the shaded region. So it's around 0.4, and it's consistent with GR plus so-called lambda cold dark matter model. That's a standard cosmological model. It's also consistent with so-called F of R theories, modified gravity theories, but it's, for example, inconsistent with the tensor vector scalar gravity theory. So that one was rejected. Now, in order to reject F of R theories, which are the best, one of the best contenders for GR, in addition to GR plus lambda CDM, you need about 5 to 10 times better measurements, and that's exactly what LSST was designed to do. So in about 5 to 10 years, we'll be doing the same test with LSST data. Here is another very nice test where these authors asked, is the cosmic acceleration the same in all directions? In other words, is the universe homogeneous and isotropic? In all these cosmological studies that I referred to until now, in all these studies that concluded that there is dark energy and so on, in all of them, we assume that the universe is isotropic and homogeneous. But we never really tested that assumption, simply because we did not have enough data to do so at high precision. So these guys had very nice idea. They said, well, we have about a few hundred supernovae. That was a long time ago, 10 years ago. They say we now plot Hubble constant versus redshift. That's bottom left diagram. That's the fundamental measurement that tells you that universe is accelerating. And now they say, well, they're scattered up and down. Let's see if we now take these two classes, those that are scattered up and scattered down, blue and red points. Let's plot them on the sky. And that's shown in the top right. Let's plot them on the sky and see and check if we see any structure on the sky. Do we see perhaps dipole distribution or some other higher order multiple moment? They did not find anything because their sample was small and precision 10 years ago of these measurements was not very high. But with LSST, we will have several million points in this diagram, and each point will be much more precise measurement than 10 years ago. So we hope that when we plot supernovae in this diagram on the sky, that we might discover some deviations from isotropy and homogeneity, or perhaps even just measuring that there are no deviations with such a large sample will give us faith in cosmological assumptions that the universe is isotropic and homogeneous. So that's another huge cosmological measurement that we will be doing with LSST. So let me now move on from cosmology to time domain studies. So, as we say in Croatian, Preradović said, u tom svijetu samo mijena stalna jest, ili tako nešto. So we know that everything is changing in the universe. And we already know from brighter surveys that objects in the universe can change position. These are asteroids, comets in solar system, but also stellar proper motions which reflect motion of stars in our galaxy around its center. And then objects can also change because they change brightness. So they don't change position, but their brightness changes. And the most significant populations are cosmic explosions that include supernovae and variable stars, where stars can change brightness either because of intrinsic instabilities or because of geometric effects such as eclipses. And so what we plan to do with LSST is to look for things that change on the sky automatically by taking every new image that we get from the camera, and we subtract it from the average of all the previous images. That would be image 1, the average. New image is image 2. We subtract them, and if nothing changed on the sky, we should see blank sky noise, like in the top right panel. Now, if there is a new object, either because something exploded at that spot, so there is supernova, or maybe an asteroid moved in that position, when we subtract it, we very easily then can see that there is an object detectable in the difference image. That's what we call alert. And we plan to execute this computation of image subtraction, search for objects, and measurement of their properties within 60 seconds of closing the shutter in Chile. The data will flow to the US, it will be processed, and there will be a web stream of alerts within 60 seconds. On average, there will be few thousand objects every 40 seconds. So per night, we'll have up to about 10 million alerts, on average about 3 million. Over 10 years, there will be of the order 10 billion such alerts. Most of them will be variable stars or asteroids, but there will be also some very peculiar explosions like gamma ray bursts that are very rare, happen once a week in LSST, or even rarer objects. So for these very rare objects, they will be filtered, and then they will be, their coordinates will be sent to other observatories where more detailed follow-up can be obtained. So if you now have new gamma ray bursts, then you would deploy telescopes in optical to get denser light curves, more data points. You would try to get spectra, and then you would extend it to other wavelengths, going from gamma rays all the way to the radio. You would try to get all your glass pointing towards that alert because they happen very rarely. That's the idea of time domain. In the same context, we also will find a lot of asteroids. So the solar system structure is another important part of LSST science portfolio. So today we know about 1 million asteroids are known in catalogs. For most of them, the data are very scarce. You barely know their color. Usually you don't, and basically just have their orbit. For about close to 100,000 asteroids, they are color data, like the diagram shown on the right, which is based on SDSS data, where these colors are real colors measured by SDSS, and they reflect the surface chemistry of asteroids. You can see that they can have different, just like rocks on Earth, they can have different surfaces going from silicates to carbonations, like interstellar dust, for example. And so with LSST, we will increase the sample size by more than a factor of 100 compared to this diagram on the right, which is state of the art today. And then not only that there will be about 100 times more objects, but the data will be significantly better. And you can see in this diagram on the left, there will be hundreds of observations compared to a few observations today. And then of course, LSST calibration will be much better. So you will be able to get light curves of asteroids, for example, and invert light curves to get the shapes of asteroids. They are not spherical, they can have elongated shapes. And because of rotation, they will have brightness variation, and then you can measure their shapes and spin rates by inverting light curves. So that will be a new field introduced by LSST. In addition, LSST will also be the most efficient finder of dangerous asteroids, of killer asteroids. Indeed, it is the only ground-based survey that can get even close to the limit by US Congress to NASA to find 90% of asteroids, near Earth asteroids larger than 140 meters. That's the limit that causes big tsunamis. And above this limit, the number of deaths in the world would be large. So that's another program that we will be undertaking. And finally, because even if we only cared about cosmology, we could not avoid looking at stars. So there will be about 20 billion stars in the catalog that will be tracers of Milky Way formation and evolution. Compared to SDSS, for example, which is gold standard today, we'll have about 40 times more stars in the sample. And as this diagram on the left summarizes, we'll see them about 10 times further away. We'll see them basically to the so-called tidal radius of the Milky Way. So these blue backgrounds are stars predicted by a simulation of Milky Way formation. And this inset in the very center is based on real data. That was a map produced by Mario Juric, another Croatian astronomer, using SDSS data. So the SDSS map shows you the extent to which we can go today. Right now, we can go a little bit further with dark energy survey that goes to the inner white circle, and then LSST will push us all the way to the end of the galaxy. And based on some special stars called RL-Lyrae that allow us to see 200 kiloparsecs even today, but not with as many stars as with LSST, only with few thousand stars. We know that there is very rich structure that is waiting for us to be discovered in detail and studied. This diagram on the bottom right is yet another Croatian astronomer, Branimir Sesar, who used SDSS RL-Lyrae to produce that map. But that map is only 2 degrees deep, so it's only 1% of the sky that it covers, while LSST will have 50% of the sky. So to summarize then, based on these 4 science themes, what the goal of LSST is basically to enable science in that domain. And to do so, we have 3 basic steps. First, we need to get images and calibrate them. That's our goal 1 and 2 here. So there will be about 2.5 million visits. Each of these includes 189 16 megapixel images. So you can think of LSST as producing 1 billion images with your phone. If you have newer cell phone, it probably has about 16 megapixels. So you would have to make billion images with your phone to be equivalent. Once we have images, we need to process them to find objects and to measure their properties. And then finally, we have to take these catalogs, the measured properties of the objects, and we want to serve them to our users. So we want to produce cutting edge tools that will enable our users to efficiently do science. We'll have about 100 petabytes worth of data. So you cannot just simply go and download the data set on your home computer and say, I'll play with it later. You have to bring your analysis methodology to our computer center, and then you do your processes there. So let me summarize these few steps. So here is illustration of what will be the change from the current cutting edge SDSS to LSST once we start getting data. So this image is color image. It's based on 3 band passes, GRI. It's about 1/10 of the full moon. It's SDSS image that goes to 22nd magnitude in astronomy speak. That's about a little bit over 1 million times fainter than your eyes can detect. And so then if you now go even further in sensitivity, then this is what you would get from LSST. This is not simulation, this is a real image. It was obtained by the Japanese Subaru telescope, 8-meter telescope, that can achieve the same sensitivity as LSST, but it cannot do it across the whole sky because it doesn't have as large field of view as LSST. So Subaru cannot deliver whole LSST, but it can illustrate what we expect from LSST. And so now I'll flip back and forth. Whenever I get tired of working on LSST and need more motivation, I go back to these 2 slides and I flip back and forth to motivate myself. This is fascinating. I've seen this 1,000 times and I always love it. So as you go fainter in astronomy, you detect more objects. And that's this sensitivity difference is why LSST will have 40 billion objects in its catalog. It will be first time in history that astronomers will have cataloged more objects than there are living people on Earth. This hasn't happened yet. All the objects that astronomers have today are perhaps 2 billion objects. So there are still more people than objects, but LSST will break that record. And also then it's not just huge numbers of objects, so not just statistics, but even if you look at specific object, you will get much better data sets. So this galaxy on the left, I usually call it boring galaxy because there aren't many details about it. But if you now get better data, and on the right is exactly the same part of the sky, that's exactly the same galaxy, but the surface brightness limit for that observation is about 4 magnitudes, about a factor of 40 fainter than on the left for SDSS. And you can see now this beautiful tidal stream that's a remnant of a galaxy that was merged, that was cannibalized by bigger galaxy. And it's significant because the shape of the tail tells us about the underlying gravitational potential. And that underlying potential is sensitive not only to the visible matter, but also to dark matter. And because of that, these galaxies that have these tails around them are excellent probes of dark matter distribution and excellent probes then of structure formation in the universe. And so today we have data like the one on the right for a few dozen galaxies. And we estimate that with LSST, the sample will include of the order 1 million such galaxies with adequate data to study dark matter distribution. So then once we have images like this, what do you do with them? So you need to process them. You need to turn them into lists of objects with measured parameters that then you can plot in your diagrams or do statistical analysis with. And so the first step is to simply remove all the instrumental artifacts. And that's what these steps on the left show. That's from SDSS. So you start in the top left with raw data from the camera. You find bleed columns, you find defects, you find cosmic rays. You correct for this, you subtract bias, you flat field, and then you find objects. And then for each object, you are measuring their brightness, their position, and so on and so forth. And that's on the right shown as circle number 1. So the diagram on the right is a high-level schematic of data management science pipelines in LSST. So there are 8 major pipelines. And what's on the left corresponds to SDSS processing, and that's pipeline number 1. But in LSST, we will have then also co-addition of images because with those 800 visits, we need to co-add them together to improve signal to noise. And then we'll also have image differencing to look for alerts, as I showed you earlier, and that's these 4 pipelines on the right. So I wish I could go into gory detail of this. Feel free to ask me questions. That's basically where I spend most of my time, is working on these pipelines and working with the team that includes about 80 people right now in data management. Altogether, it will be about 500 person-years of effort to develop these few million lines of code. And then finally, once we have these catalogs, we need to serve them to the users. And this is a design of our LSST science platform. So this is basically designed by Mario Juric. He was the head of this team when this was designed. So the most significant difference compared to other surveys like SDSS is that in addition to portal, we'll also have ability for you to upload your notebooks. For example, IPython notebooks that you can upload to our data center. And then instead of downloading data to your computer, you will do all your analysis, all your programming of your analysis in our data center. And it will appear to you as if you were doing it on your own laptop. And then there will be also web APIs where you can plug in your code to talk directly to data center. You will be able to do many other things that like you did in SDSS and many more. So all this together is leading to a new paradigm in astronomy where you don't go anymore to a telescope. So I always loved this cartoon. Even during days of SDSS, it was relevant because there is a growing fraction of astronomers that don't go to telescopes anymore. They don't make instruments anymore. They simply log in to a big database of a survey and then do some science with this publicly available database. And it's a huge change in paradigm, not just because you don't have to do observations yourself, but also because you don't go through the classic science questions of, I have some hypothesis, I want to test it. What data do I need to get? That's classical science. With this survey astronomy, it's the opposite. You have this giant database, and then you ask, given this data, what theories or hypotheses could I test? So it's the opposite. So I paraphrased John Kennedy, who said, ask not what you can do for your country, ask of what your country can do for you, ask what you can do for your country. So this red statement up there is stolen from Kennedy, but nicely illustrates that it's completely new way of thinking once you have giant survey databases and you do science with them. So now that I gave you this quick summary of science and goals behind LSST, let me spend a few minutes on showing you a few photographs of the observatory itself and where do we stand with the construction. So construction started in 2014 after 10 years of preparing everything, which included designing the science program, then translating science program into engineering design of the observatory and software system, and raising the funding from federal agencies and from private donors. So that took half a decade. First, we needed to get most of the community behind us in a process called Decadal Survey of Astronomy, where LSST was ranked as #1 priority in ground-based astronomy. And because of that ranking, then federal agencies approved the construction of LSST. And then it also helped us raise some early money, for example, for primary mirror from Bill Gates and a few other people who worked for Microsoft. So that process took 10 years. And then once we got federal funding, then we could start with the construction in its earnest. And so in about 2 years, we came to this point that was late 2016. You can nicely see the structure of the observatory. There are 6 floors and the dome is on the right here. It wasn't yet installed. Here is me doing so-called Baustelle, checking things that they are in Wasserwaga. So everything was fine. That was a little joke. And then a couple of years later, we got the dome installed. The dome was procured from an Italian company. And just as we thought dome would be completely enclosed, we had to shut down due to COVID. I'll show you another photograph later. So here is a design of the telescope. You can see that it's very short telescope. It's not like astronomical cartoons when you have astronomer in white lab coat looking through a very long and thin telescope. That would be refractor, but today we use reflectors. And LSST is special because it has to move very rapidly. We do not want to waste time on acquiring new field and spending a lot of time slewing across the sky. So this telescope is designed to slew and settle for next exposure in 5 seconds. And so during that motion, it draws about 1 megawatt of power, which is of course much more than the electric lines can bring to the summit. So in order to run it, we have capacitor banks that stored the charge over 30 or 40 seconds during exposure, and then use that charge to move the telescope to a next field. So essentially it's a big battery. You could call it a battery operated telescope because of these capacitor banks. The telescope was designed in US by our team, but it was constructed in Spain, a company Astrofito and their contractors. So it was completed and tested in Spain in the fall of the last year. And since then it was disassembled, shipped to Chile, and we started reassembly about 3 months ago. And that was going well, again, until about a month ago. Here is the mirror. The mirror is 2-surface mirror. This is when we took it out from the oven. This red edge here, that's the wall of the oven. This is spinning, and you can heat this glass that you put in until it's melted. And then because of rotation, the top surface, this surface is parabola, and then you cool it down until it's solid again. And that takes about 3 to 4 months. And then at the end, you only need to polish these inner parts for tertiary mirror. But because the initial surface is parabola, you save a lot of effort and a lot of money on polishing the telescope. So that's how it looks after polishing. So this outer part is primary mirror, and you can see here this line, that's the border between the outer primary mirror and this inner tertiary mirror that has different figure here. And this hole in the middle, that's simply to let water out when we wash it every few months. Here is the camera. The camera will be the largest camera ever constructed in astronomy. It will be 3,000 megapixels. It will be fairly large. You can compare it here to a person. It's rather complicated. Here is a slightly simpler way to look at it. So there are 3 lenses in the entrance to the camera. Then there is a filter exchange mechanism. So you can see filters here. Each filter is almost a meter large. And then there is focal plane in here. So that's where CCDs are, where 3 gigapixels are found. And then here is a utility trunk and cooling and so on, cryostat. So the entrance lens is about 1.6 meters. It's the largest lens ever produced, at least publicly known lens ever produced. It's bigger than the Yerkes lens. Yerkes telescope is the largest refractor in the world, but this lens is 1.8 meter. Yerkes is just 1 meter. So that was a major undertaking to produce such a flawless lens. The focal plane is based on a modular design. So in order to get so many pixels packed into the camera, they are organized in 3x3 CCDs. Each these small blue squares are 1 CCD, and this 3x3 red square is shown in here, that so-called raft. It's essentially an autonomous camera because all the electronics are underneath these 9 CCDs and are fully replaceable. So if one dies during the operations, we have spare rafts that can go in. So this way you can achieve this huge pixel count, and also we need very short readout time. So we can read out in 2 seconds. And that's because each CCD is not only read individually, but within each CCD, there are 16 segments that are read out at 500 kilohertz. And that's how you get this amazing readout time of 2 seconds. Astronomers know that that's super fast. Typically, it's several minutes to read your image on a large format focal array. And a couple of months ago, we completed integration of the camera. Early in the project, as recently as 3 years ago, the main risk, or one of the main risks, was, are we going to procure all the CCDs that we need? These are 189 CCDs, just the CCDs. Each of these little squares is about 1,000,000 kunas device. It's very expensive and it's custom made. It wasn't obvious that we would get all of them on time. So in the end, we used 2 vendors. So that's not risk anymore. And finally, a few months ago, we managed to integrate them all in the focal plane. So we started cooling it down, and we were just about to make some test image and have a press release that the camera is essentially complete, when again, we had to shut the SLAC laboratory down and didn't finish it. Here is just illustration for public outreach. What does it mean to have that many pixels? So if you adjust the pixel size to your eye resolution, as it was done in the design of high definition televisions, then in order to display all these pixels, you would need 1,500 high definition televisions. That is how much data there is in just one single image from LSST. Here is another shot in the lab, in the clean room, at the assembly of the camera. And as I said, a few weeks ago, or about a month ago, we had to shut it down. So that's the current state. There are no people at the summit. We have 2 people going once a week to make sure that the wind didn't blow away those tarps. But basically, we are now in standby mode until the crews from Italy and Spain can return and complete the cladding on the dome. You can see we just needed 2 more weeks to be done with the dome, and we didn't finish it. And then the reassembly of the telescope under this big tarp was going extremely well, but then again, we had to stop. So I already showed you this joke. So what do you do now that you don't have a telescope, but you have database? How do you process this data? So I think I have a few minutes left. So let me quickly go through a few slides and end with some shameless advertisement. So first, why is it hard? So if imagine you were talking to statisticians or mathematician or computer scientists, complaining how hard it is to do analysis in astronomy with LSST, what would you tell them? Well, the top list of difficulties that you face if you want to play with this 100 petabyte LSST data set is, first, it's large. It's not so easy to shuffle petabytes around. It takes disk, it takes time, it takes some tools to do so. Then if you want to study objects, billions of objects is also a big number. Like if you wanted to do it in Excel spreadsheet, obviously that's not going to work. So you will need to do some custom designed, custom-made code. Then once you start doing your statistical analysis, then you quickly realize you are working in highly multidimensional spaces. I will illustrate that in a moment, but we have thousands of dimensions. Then often you don't know what statistical distributions you're working with. In most statistical tests, for example, you assume you have some statistical distribution and then you design an optimal test. But here we have unknown statistical distributions. Then if you're working with time series data, there are literally tens of thousands of books written by engineers about analysis of time series data. But essentially 100% of those books from engineering assume regular sampling because that's what machines and instruments do. They regularly sample something. But in astronomy, of course, we have day and night cycle, we have rain, we don't have regular sampling. And that opens a whole slew of new problems. Then we have things that are called truncated or censored data in statistics, where, for example, you look at some point on the sky and you don't detect that object because on that day it was below your sensitivity limit. Then there is also issue with so-called heteroscedastic errors, which is a great word to use at parties. The opposite is homoscedastic error. So homoscedastic errors are errors that are always the same. And if you do just your undergrad lab in least square methods, that's what formula you would get. But then if your errors vary with each measurement, that's called heteroscedastic errors. And often they give you a lot of trouble when you want to apply traditional methods. And then, of course, in astronomy, we also have often unknown systematic errors that one has to be worried about. Like the simple thing is you measure a light curve of your star and everything looks nice and your errors are Gaussian and you fit some model and then you have a data point that is off by factor of 100. And that screws up your entire fitting. And then you ask yourself, what happened? Why is it so bad? And then it happens that there was some silly asteroid on top of your star, just happened to be exactly on top of it. It wasn't resolved. So the only effect is that your star became much, much brighter. And now your fitting code is going crazy because it doesn't know that. So there are lots of these problems and it's not trivial how to handle them. We really need to train new generation of students, new generation of astronomers to be able to handle such huge data sets. And so here is that illustration of highly multidimensional spaces. So we will have about 40 billion objects in LSST, and they will be measured of the order 1,000 times. We have about 1,000 visits. In each visit, we will measure position, we will measure brightness, we will measure shape, we'll measure about a few dozen parameters. And so let it be just 10. So 10 times 1,000 measurements, that's 10,000 numbers. So your measurements will span at least 10,000 dimensional space, and that space will be populated with 40 billion points. So that sounds like a lot. The diagram, the image on the left shows three-dimensional space with three principal vectors, and it shows some morphologies like donut or the thing with the hole, toroidal distribution, then used bubble gum, then like tooth or whatever you want to call it. There are different morphologies in this space. And we already today have mathematical methods from computer science that can handle this easily in 3D and find these morphologies. Basically, they correspond to different populations. Then we want to characterize these populations. And then finally, you want to look for things that do not look like anything else. that red question mark, those dots, they are some kind of unusual objects, some outliers, some anomalies. So we already have a good idea how to do that in lower dimensionality spaces with millions of points. What we need to do is to scale our methodologies to much higher dimensional space. And there is something in machine learning called curse of dimensionality, which often bites you. So we have to scale up our methods to higher dimensional spaces, and you need to scale it to a huge number of points. Many methods are n squared, for example, where n is number of objects. And unless they are n log n, there is no way to execute n squared once you have billions of objects. It would take computers hundreds of years to do it. So that's the problem that we are facing. But what we want to do with these spaces, surprisingly, can be summarized as a very small number of goals. And basically there are three. You want to find clusters. You want to classify objects given this data, basically to assign them to clusters. And finally, you want to be able to look for things that don't behave like the rest of the population. So here is one example. I'm using sheep, but I could use as well galaxies. But what I'm trying now to find out is which of these sheep is different than the other ones. I'm looking for my outlier. And you may guess, oh, this sheep in the blue sweater, that's your outlier. And I would say, no, that's just a different population of sheep that likes blue sweaters. What I'm really looking for is this guy. You see this red circle? That's anomalous sheep. The only difference between that one and the other sheep is that its right eye is open. So it's very tiny thing. At the beginning, you often don't know what you're looking for. And then you can have confusing populations like that sheep that likes blue feathers. This is just an illustration. But we face the similar things. So I would love if I had more time to go into more detail, but I don't. So I will just end with shameless advertisement for this book that describes many of these methodologies from the astronomical point of view, but it's definitely applicable to other branches of physics. If you're interested in data mining, in machine learning, if you're interested in how to process large data sets, and if you're interested in learning more Python, then I highly recommend it. So I will end here with these conclusions, and then I'll stop sharing and we can go to questions. So if there is one thing to remember from this talk is, especially if you're not an astronomer, is that today astronomers are detecting and measuring billions of objects. And from that fact, then you can, as a good physicist, you can back engineer everything about astronomy you want. What kind of instruments we must have, what kind of problems we face. Just if you realize that today in astronomy, we are not looking at individual objects anymore. We are detecting and measuring literally tens of billions of objects. And of course, that's not trivial. So to accomplish this goal, you really need not just astronomers, not even just astronomers and physicists, but also other professions, computer scientists, and most notably mechanical and electronics engineers to design the cutting edge instrumentation. And you need lots of money too. And lastly, because we are working with tens of billions of objects, and because of rapid development of computer technology, just as in many other fields in astronomy, data mining and machine learning are also playing an increasingly important role today. So I will stop here and let me stop sharing and we can talk about questions.